Next talk is by Owen Conoly. Owen is an undergrad, so he's looking for a PhD. He's going to apply for PhD in the upcoming cycle. And we will hear about not defining constant time, but proving constant time in the context of a verification framework in ROC. Thank you.
Hello. Thank you for the introduction. So I'm going to be talking about mechanical verification that compilers preserve cryptographic constant time. So I'll begin with a quick review of what I mean by constant time. So we say that a program accumulates a leakage trace as it runs, consisting of branches taken by the program along with addresses of reads and writes to memory. So for example, this guy on the left here, we say that the leakage trace of this consists of a store at address A, followed by a load at address B. And the thing to note here is that the addresses go in the leakage trace, but the values loaded do not. And this guy on the right, well, we just leak a 1 or a 0 corresponding to the program leaks a 1 or a 0 corresponding to the direction of the branch when it runs. All right. And then we say that a program is constant time if its leakage trace is independent of any secret values held by the program. And the point is that if a program is constant time, then an adversary cannot learn any of the program's secrets by reading the leakage trace. So the project that I'm going to describe here, we wrote a proof in ROC that a compiler for a C-like language is constant time preserving. Where by constant time preserving, I just mean give it a constant time program as input, you get a constant time program as output. And the point is that we can use this compiler theorem to compose it with theorems saying that source programs are constant time to obtain final theorems saying that individual RISC-V machine code programs are constant time. So past work has shown how to prove that compilers preserve constant time, including this work with Jasmine and CompCert that I have on the slide here. And some very recent work has actually shown how to prove that compilers preserve a speculative notion of constant time. In contrast, we do not worry about speculation. So what do we do then that is new? So all the past work just works with compilers where the source and target languages are deterministic. And this is because it's not so clear initially how to even define a reasonable notion of constant time for non-deterministic programs. So our work gives the first notion of constant time for a language with compiler-resolved non-determinism, where what I mean by compiler-resolved is that we have some non-deterministic construct that is present on the source level of our compiler, but it disappears on the target level. Like our example that we'll talk about here is memory allocation non-determinism. You have things like non-deterministic stack allocation on the source level, but this does not appear with machine code. And so to make it feasible for us to write constant time proofs about non-deterministic compilers, we find it very convenient to state constant time in a simplified, unconventional way using no hyperproperties and a non-traditional style semantics that I'll talk about later. So a pictorial summary of the project here. So our source language, Bedrock2, is a subset of C with simplified memory semantics. We just say that pointers are machine words and memory is a map from machine words to bytes, which is nice. And Bedrock2 has all the important things that you see in C, like loops and functions. And interestingly, for our purposes, these non-deterministic constructs of stack allocation and runtime input-output. So the idea here is that we can write a source proof in ROC that a source program is constant time, and then compose that with our compiler theorem to obtain a final theorem saying that the RISC-V machine code output by the compiler is constant time, where so that our trusted code then of our final theorem is only the formalization of RISC-V semantics and the leakage traces on the RISC-V level. All right. So I want to talk about specifications saying that compilers preserve constant time, but I'll start by just talking about specifications of functional correctness for compilers with non-deterministic languages, because it turns out that's interesting. And to do that, I'll start by talking about a nice way of writing down semantics for non-deterministic languages. So this has been called omnisemantics in past work. So the main difference between this and usual big step semantics is that instead of talking about programs running to final states, we talk about programs running to postconditions. So for a postcondition Q, we say that program P with initial state S runs to the postcondition Q if the program always terminates without crashing in a final state satisfying the postcondition. Or we can think of postconditions as sets of allowed final states, in which case we just say it should be an element of that set. So this is a variant of weakest preconditions semantics, which hopefully you've heard of. So the main difference between this and usual approaches to weakest precondition semantics is that we define this down arrow, or PS running to Q judgment inductively by rules analogous to traditional big step semantics. And this is very nice because it allows us to write nice inductive proofs by induction on this judgment, just like as you would write proofs by induction on a usual big step judgment. And so why am I talking about omnisemantics? Well, the reason we care about it here is that it makes compilers proofs easy, as the slide says. So I'll begin by reviewing the case for non-deterministic languages. So with traditional big step semantics, we can write a forward spec when the sourcing languages are deterministic. And this just says that if you have a source execution, then you have a corresponding target execution. Going from source to target is why we call this forward. And with omnisemantics, the corresponding specification you write is that if the source program runs to a postcondition, then the target program should run to a related postcondition. So clearly this is just saying that the compiler preserves specifications, which is, so it, the compiler is functionally correct. Now with usual big step semantics, with non-deterministic languages, compiler specifications get a bit more complicated because you need a backwards specification saying that any possible target program execution corresponds to some related source program execution. On the other hand, with omnisemantics, we can still have the same specification, and this is still meaningful. So we just say that if the source program admits a certain postcondition, then so does the target program. And yeah, so clearly this means functional correctness. And so the reason I'm talking about this is that forward specifications are nice. They're easy to prove by induction on the source program judgment, deriving the target program judgment as you go. On the other hand, the backwards specifications are a bit not so straightforward to prove by induction on the hypothesis because, well, how do you do induction when you have the output of the compiler C here? You somewhat have to do something like invert the compiler C, and that is hard. So in summary, omnisemantics gives us an inductive definition of this program running to this postcondition, which it allows easy forward compiler proofs. And this is particularly relevant for what I'm talking about now because the Bedrock2 compiler proof that we extend in this work to say things about security properties uses omni big step semantics, which is this down arrow judgment I have here. All right, so having finished reviewing relevant past work, I'll go on to new stuff that we did here. So beginning with a formalization of constant time for deterministic programs. So for a deterministic program P, we'll write spub to denote the public part of an initial state of the program, and I'll say what it means for P to be constant time. So the conventional way of stating this is that P is constant time if for any two initial states with the same public parts, these should lead to the same leakage trace of the program. So this is, should be intuitive, exactly straightforward formalization of our informal notion of constant time. But this is a hyperproperty, meaning that it relates two different executions, one starting with the state S1, one with the state S2. And hyperproperties are generally difficult to reason about, and in particular, particularly relevant for us here is that it's unclear how to state a hyperproperty with omnisemantics just because, what do you say that the postcondition should be? So we are interested in what I'll call a single copy definition, which is just a definition that only references one execution at once, rather than referencing two, as this definition up here does. So an alternative and equivalent way of formalizing constant time is to say that P is constant time if there exists a function f that takes its input the public initial state and gives you the leakage trace of the program. So these are obviously equivalent, but I emphasize the difference just because the second will be much more convenient for us because we can state it using omnisemantics with a single postcondition. of the program. So here's an example of writing a specification, a constant time specification of a program using omnisemantics. So here we have a swap program, takes 2 pointers, swaps the values of the pointers. We'll say that the pointers themselves are public inputs, whereas the values stored at the pointer, at the addresses, are private. And in that case, we have this specification here. So just to explain the syntax here, we say that this program is running to this set of possible final leakage traces. It's a singleton set consisting of the result of applying the function f to the public data here, which is the pointer A and the pointer B. And so the key point here is just that the final leakage trace here depends only on pointer A and pointer B, and in particular is independent of these values A and, or the values stored at the addresses. And we can straightforwardly prove specifications like this just by instantiating the function f appropriately that is claimed to exist. And by looking at swap, we can see, well, what is its leakage trace in terms of A pointer and B pointer? Well, we load at A pointer, load at B pointer, so on. Okay, now things get slightly more interesting when we have non-deterministic programs, and we would like to say what it means for them to be constant time. So our definition of constant time for deterministic programs requires that for every initial state, there should be at most one corresponding leakage trace of the program, right? And so non-deterministic programs are not going to usually satisfy this definition because if you branch on any non-deterministic values at all, then you'll have multiple possible leakage traces per public initial state, right? Nonetheless, I claim there are non-deterministic programs that we might want to call constant time. So we have this toy login function here. Takes an input, checks whether it is whether the password input is correct, and now the leakage trace of this login function is going to be non-deterministic because the leakage of this lookup password function depends on the input to it, and this is a runtime input that is we model as being non-deterministic. So certainly this is not going to meet our definition of deterministic constant time because the leakage trace is not going to depend on public initial state. So we have a straightforward definition of this, exactly what you'd think it'd say. We say that a program is constant time if the leakage trace of the program is a function of, well, now it gets to depend on not only public initial state, but also any public inputs during the execution. So again, just saying that leakage trace is a function of public values. And right, so we can straightforwardly write a specification of saying that the login function is constant time. So again, explaining the syntax here, this set here is a set of final possible tuples of input-output trace accumulated during the execution and leakage trace. So we're saying that the IO trace should consist of a username being input, a password attempt being input, and then something being output. And we're just saying that the leakage trace here should be the function f of the username that is input. In particular, it does not depend on the password attempt A or any secrets that might be stored in the memory M. Now, where things get quite interesting is where you have compiler-resolved nondeterminism, like our memory allocation nondeterminism that we mentioned earlier. So consider this program, which is, it looks harmless, it does nothing. So this swaps 2 values in an allocated array. So certainly we want to call this constant time. It looks quite harmless from a security point of view. But it does not meet our deterministic definition of constant time because the address S is non-deterministic. According to our Bedrock2 semantics, we say that memory allocation addresses are non-deterministic. So yeah, will not meet our deterministic definition of constant time. So how do we generalize our notion of constant time to say that programs like stack swap are constant time? So a bad idea would be to treat this in the way that I just showed you to how to treat runtime I/O. So we could keep a log of memory allocation events, and then we could write postconditions saying that, well, since surely the memory allocation addresses should be public data, the leakage trace could depend arbitrarily on memory allocation events kept in this memory log. So the problem with this is that for bigger programs, postconditions would get extremely complicated if maybe you have memory allocations interleaved with loops and function calls and whatnot. And a more fundamental issue is that it's unclear what a compiler theorem would say about the memory allocation log, precisely because it is compiler-resolved nondeterminism, right? So it's not preserved by the compiler. For the case of runtime I/O, well, we just say the compiler should preserve that, but here we can't do that. So in our paper, we explore two generalizations of constant time to say that stack swap is constant time. One is to say, well, compiler-resolved nondeterminism causes problems, so let's get rid of it, and determinize memory allocation in a somewhat unobtrusive way. And another approach is to formalize a notion of leakage trace modulo compiler-resolved nondeterminism, so that we can formally say that constant time programs are those for which leakage trace modulo compiler-resolved nondeterminism is a function of public values. And yeah, so in our paper, we show that both of these approaches work out nicely, and we use both of these approaches to prove that the Bedrock2 compiler is constant time preserving. We also prove that these two notions of constant time are equivalent in a very strong sense, but we note that there are some interesting differences between the compiler theorems you would prove in these two approaches. And yeah, and that is all I have to say. So I'll take questions now if there are any.
Thank you. Any question?
I have a question about the constant time semantics. So there are many cryptographic algorithms which are not strictly secret independent. They leak a very small amount of information about your secret, and that's not considered a vulnerability. One example is rejection sampling. You take a secret and a counter, and then you produce some random seed deterministically based on your counter and the secret. And then you do some operation with the seed and see if it succeeds. And if it fails, you take another seed and try again. That's rejection sampling. And then your execution time would leak the information that you attempted that many times before you succeeded.
I see.
And that's a secret dependent. But that's usually not considered to be a vulnerability. So in PL terms, this means in the middle of these algorithms, you often have to say, we can declassify some amount of your secret state into public state. So do you think it's easy or challenging with your new constant time semantics to specify, say, in the middle of algorithm, it's okay to declassify part of your secret state and make it public so you can leak that information safely?
Yeah, so I'm almost certain that I understand what you're saying. And so you're saying that is it okay to leak some function of like the thing that initial state that you would usually consider private, yeah. Right? So yeah, that's easy to express using this. All you say is that, say that the final leakage trace only depends on this function of the private data that it doesn't reveal very much.
I see, thank you.
I have maybe a question myself. So you define a new definition for constant time, and at the same time it seems like it's related or close to the definition that people use. It's just that it's more convenient for omnisemantics. In the omnisemantics papers, there is equivalence between omnisemantics and other traditional kind of semantics. Have you thought about proving that your notion of constant time correspond to a hyperproperty kind of constant time on the other semantics?
No, I've not bothered, but it seems like it would be easy to prove.
Okay.
Yeah.
Hey, Rohan from Stanford. I was wondering if you could just explain a little bit more about the difference between the bad idea and the option number 2. Because kind of reading them, I don't think I was able to kind of discern the subtlety of why one of them is a good idea and one of them is a bad idea.
Yeah, so I guess this option number 2 here, it certainly can be viewed as a variation on the thing that I've called a bad idea. But yeah, I guess it turns out to be somewhat subtle how you formalize this notion. And also, the difference I had in mind between what I have here and the bad idea is that here we are doing it in a systematic way. Whereas with our approach with the runtime I/O was to just kind of write ad hoc specifications one by one. But it's important to do it in some systematic way and have a general definition of this leakage trace modulo compiler resolve nondeterminism so that you can write an appropriate compiler theorem about it, saying that this is preserved when you push it through the compiler.
Okay, thanks.
Yeah.
Maybe one last question. So it seems at some levels that your strategy is not really specific about constant time. It's about leakage of any trace, or preservation of any trace, because you don't really have a notion of time on the source, no time on the target. They're all about a trace of events. Have you thought about generalizing it for other kind of hyperproperties, not about time, but about other kind of security properties or something?
I have not thought about that much, no, but I definitely agree with you that there seems to be very little about, or nothing about this approach that's specific to the notion of time, and it would be very interesting to explore generalization to other things.
Okay, thanks. Thanks. Oh, no, there's one more question. Yay.
Yeah. Hi, I'll ask one question. So, not being super familiar with all this constant time stuff, I wonder how the definition differs from non-interference?
Yeah, so I think it's very similar. The difference being that I think with constant time we have this extra data of the leakage trace, and you're saying that that's independent of secrets, whereas generally with formalization of non-interference that I've seen, you just talk about, say, private parts of memory or some state that's already in the computer, and you just say, well, this final private part of the memory should not depend on the yeah, you say what it's. Or did that answer your question?
Not quite, to be honest, because you're like two initial states. Is the state not memory?
Oh yeah, so. Absolutely. So here with constant time, we're saying that the final thing that the leakage trace does not depend on private values, whereas traditionally with non-interference, you'd be saying, oh, the private memory does not depend on, the public memory does not depend on private values.
But I'd also like to suggest that you can see this as a special case of non-interference when you work with an instrumented semantics that maintains this leakage trace and then otherwise treats it as any other state that you might see in old school non-interference.
Okay, let's thank our speaker again.